All right, so in the last lecture, we learned how to calculate the frequency or the time period of physical pendulum. And the expression was omega equals square root of mgl divided by I. And from there, of course, you can write down an expression for the time period too, because time period is 2 pi divided by omega. So that's going to be 2 pi square root of I divided by mgl. I mentioned that it's important to remember two things about these expressions. What is I? I is the moment of inertia about the axis through the pivot point, and L is the distance between the center of mass of the object and the pivot point. Right? So these are the two things that you need to remember when you're using these expressions. So I'll just do a couple of examples just to show you how you can use these expressions. So let's calculate. Let's start with something really simple. Let's calculate the time period of a simple pendulum. So we've talked about the physical pendulum. I told you what a simple pendulum is. A simple pendulum just consists of a massless string of length, let's call that little l, and a point mass m, and the point mass doesn't have any spatial extent, and the massless string obviously by definition doesn't have any mass. So what is the time period of this going to be? So if you swing this out to a certain distance, and remember that our entire analysis relied on this angle being small, so our results apply when this angle theta is small, so it's like not more than 10 degrees or something like that. It's most accurate when it's less than 10 degrees. It will still be approximately accurate for even for 30 degrees or something like that. But if you want accurate agreement with experiments, then you want this angle theta to be smaller than 10 degrees so that the small angle approximation that we used is valid. All right, so we want to find out the time period, which means the time taken for one complete swing. So if you're starting from this end, then the time taken to go all the way over here and then come all the way back. That's what we are trying to find out. So we already have our formula for anything that's oscillating, the physical pendulum. So we just need to find out the I for this and the L for this. So for this system, the I would just be the moment of inertia of the point mass m about an axis which passes through the pivot point. So what is the formula that we're going to use? The moment of inertia of a point mass, as you know, is just going to be mr squared. So in this case, it's going to be m multiplied by L squared. So that's the moment of inertia of a point mass at a distance L from the axis of rotation. So that was no problem. What about the capital L? So we figured this out. What about this capital L? So the capital L is the distance from the pivot point to the center of mass of the system. So our system is just one point mass. The string doesn't have any mass. So our system is just one point mass. And so obviously its center of mass is just the point mass. So, so our L is capital L is just little l. So the L is just little l. And I is ml squared in this example. Okay. So we can just plug these in and get the time period. So the time period is equal to 2 pi square root of ml squared divided by mg times little l. You can simplify this a little bit. And then you get this very famous formula, T is equal to 2 pi square root of L divided by G. This is the time period of a simple pendulum, right? Okay, one curious thing about this is the following. You might imagine if I had asked you a question that in a simple pendulum, what would happen if I double the mass? So instead of m, suppose I've got 10m or 100m, and I give the pendulum, I swing it to one side and let it oscillate. How will the time period be affected? you might have thought that the time period would either increase or decrease, but as it turns out, that's not what happens. The time period does not depend on the mass of the bob. The time period only depends on the length of the pendulum. And it depends on g. These are the only two things that the time period of the simple pendulum depends on. There's a story about this. This little fact was first discovered by Galileo, very young Galileo, when he was probably around 14 years old or something like that. He was sitting in church and he was watching the chandeliers swing. So there were chandeliers of various lengths which were swinging in the wind. And Galileo was watching those swing, and he suddenly had this realization that the time period did not depend on the mass of the bulb. It just depended on the length of the bulb, of the cord suspending it. And it is said that he did not just like to accept facts just because they appeared to be true. There was no clocks at that time, so he used his wristwatch. He used his pulse, not his wristwatch. He used his pulse to measure the period of the chandeliers, and he verified that statement is indeed true. And that ultimately gave him the idea of creating a device that can accurately measure time. So how would a pendulum measure time? You know that each swing of the pendulum is determined only by one thing, which is the length of the pendulum, right? So if you standardize the length, if you standardize a certain length, then it's the time it takes to swing is standardized, right? And so you can use that to measure out time. Like one event consists of 7 swings of this particular pendulum. So that would be true for anybody who's using the same length for the pendulum. So this was the idea of a pendulum clock, which Galileo had when he was very young. And he was preoccupied with a lot of other things throughout his scientific career, mostly astronomy, mechanics. It was only after he was put to house arrest by the Catholic Church, and he was forbidden from doing astronomy. And so at that time, he came back to this idea which he had when he was a little kid. And with the help of his son, he built the first pendulum clock. All right, so that is this formula. All right, we'll do one more example. Suppose you have a physical pendulum. So this is on slide 16, the second example on slide 16. Suppose you have a physical pendulum, which is made up of a uniform rod of length L and pivoted at one end. So our physical pendulum now consists of a uniform rod. And we want to find out its time period. So the time period of that would just be 2 pi square root of I divided by mg L. So it's again just a matter of making sure you're putting in the correct I and the correct L. So let's say that the length of this rod is, let's just call it little l, unlike what I have on the slide, so I don't mix it up with the capital L in the formula. So the length of the rod is little l, right? And let's say that the mass of the rod is m. Okay, so we need to figure out what I to use. So what I should it be? Feel free to pause the video and see if you can figure out the correct I. So this rod is rotating about an axis which passes through the pivot point. That's the I that we need to use. So that I would be 1/3 ml square. So we need to do 2 pi 1/3 ml square. And in the denominator, we've got mg, and then we need to use, we need to figure out what the capital L is. So once again, pause the video and see if you can figure out the correct capital L to use. Capital L is the distance from the pivot point to the center of mass of the system. And so the center of mass of a thin uniform rod obviously is at its center. So our capital L is just little l divided by 2. So if you simplify these, the m's cancel out, one of the l's cancels out as well. So if you simplify this, you get the answer, which is 2 pi square root of 2L divided by 3G. That is the time period of a physical pendulum, which consists of a rod. I'll do one more example. In class, these are the only two that I do, but then I find that a lot of students come to me with one particular problem from mastering physics, so I might as well just discuss that over here. So if I remember correctly, the problem in mastering physics wants you to find the time period of a physical pendulum, which consists of two rods which are on a support. So there's a support sort of thing over here. So you have an L-shaped structure made of two rods, which are my black lines here, and they're placed on this support, which is the blue triangle. And you could swing this to one side, and then it's just going to oscillate. The L-shaped structure is just going to oscillate back and forth. Let me see if I can do it with my fingers. Okay. So, right, you have to find the time period of that, right? So again, same thing. The formula is T is equal to 2 pi square root of I divided by MGL. I would be the moment of inertia of the two rods about the pivot point. So the pivot point, let's just name that O. So the moment of inertia of the two rods about the point O, you know exactly how to do this. You've done problems like this in chapter 10, moment of inertia. So that would be, so what's the I going to be? Let's just write that down. So the I, this is two rods. Let's say each of the rods has mass M. And length little l. Maybe I'll just make the mass little m. So each of the rods has mass m and length little l, right? That's given in the problem. So what is the moment of inertia of each rod going to be? So each rod, the moment of inertia would just be 1/3 ml squared, and you've got two of them. So it's going to be 2 times 1/3 ml squared. So that's our I. All right. And what about the L? So for L is the distance from the pivot point to the center of mass of the system. So where is the center of mass of the system? Okay, pause the video and see if you can figure that out. Where is the center of mass of this L-shaped object? One way of thinking about that is this. You can think about where the center of mass of each of these rods is going to be. It's going to be at the center of each rod. And where is the center? And so both of these rods have equal mass. So where is the center of mass of these two point masses going to be? So for a moment, just replace these rods by a point mass sitting at their center, which is what the center of mass is. So where is the center of mass of these 2 point masses? They have the same mass. So their center of mass will just be at the center of the line joining them, right? That just comes from the formula m1x1 plus m2x2 divided by m1 plus m2. Okay, so the center of mass would just be at the center of these 2 points. So we just need to find this distance. Let's make that a different color. We just need to find this distance. How do we find that? That's just geometry. So this length is going to be L over 2, right? The problem tells us that the L-shaped structure makes a 90-degree angle. So that means this angle here is 45 degrees. So the red length, which is our L, might as well write that. That's the capital L that we are interested in. It's just going to be little l over 2 sine cosine 45 degrees. So our L is little l over 2 cosine 45 degrees. Cosine 45 degrees is 1 over root 2. So L divided by 2 root 2. So we've successfully found both I and L, and now you can just plug them into the formula and get the answer. So I would be 2/3 ml squared, and divided by, oh, and what should I use for the m here? M is the total mass of the system, right? So what is the total mass of our system? The total mass of our system is 2m, right? Because you've got two rods. So what goes in over here is 2m, because that is the total mass of the system. So that's why we put in 2m, because we've got two rods of mass m. Okay, so you have that, and then G, and then the capital L we just found is L divided by 2√2. And then you just need to simplify this expression, and you would get, you'll get the answer. All right, so we did a few problems on physical pendulums. We just have two more topics in this chapter, which I'm just going to very briefly go over. So we talked about simple harmonic motion, completely ignoring friction. So, but in the real world, you know that any system that's oscillating will encounter friction, and you know exactly what that's going to do. It's going to cause the object to slow down and eventually stop. Right? So this kind of harmonic motion where you have friction or non-conservative forces acting is called a damped harmonic motion. Right? So we are not going to get into the mathematics of damped harmonic motion at all. And so you can just ignore these equations over here. I'll just briefly introduce you to the mathematical expression that you get. So this turns out to be the differential equation. The damping term is represented as a term that is proportional to the velocity of the simple harmonic oscillator. So this F is the damping force. It's minus constant times the velocity. And so that's inserted in our differential equation. So this is just Newton's second law. On the right side, you've got mass times acceleration. On the left side, you've got force. The force consists of the force due to the spring and the force due to damping. So this is the spring force. This is the damping force, or the friction force. And so this is a differential equation that you get when you want to take the damping into account. And this differential equation obviously is much more complicated than the simple one that we've treated in the chapter. It's possible to solve this differential equation. If you solve it, you get a solution that looks like this. And this is one of the solutions that you get. Let's just try to understand what this solution is telling us. So this part looks familiar. This is part of the equation of motion of a simple harmonic oscillator. So cosine omega t plus phi tells you that x is going to oscillate back and forth, right? However, the amplitude is not constant. You can see that the amplitude is multiplied by an exponential factor, e to the power of minus something times t. So as t increases, the e to the power of minus t, e to the power of minus something times t gets smaller and smaller. And so you can see that the amplitude will gradually get smaller and smaller. And that's what you can see happening over here. The amplitude is getting slower and slower, smaller and smaller. And eventually the oscillation dies down. So it keeps on oscillating, but with a smaller and smaller amplitude. And then the oscillation dies down. So that is damped oscillations. If you take a differential equations class, then you will probably see this kind of differential equation and learn how to solve them and investigate its various solutions. And if you take a more advanced physics class, then you will study damped oscillations in a lot of detail. All right, the last thing that I'm going to briefly mention is that is forced oscillations. So far we've talked about systems where there is no force which is forcing it to oscillate. So in other words, if you just take the spring mass system and you displace it a little bit, then it's going to start oscillating. The mass is going to start oscillating, and the frequency is determined solely by properties of the system itself. So what does the frequency depend on? Omega is equal to square root of k over m, as you know. So the frequency depends on the stiffness of the spring and the mass. These are the two things the frequency depends on. So this is called the natural frequency of oscillation of the system. Natural in the sense that you're not making the system oscillate in any way. You're just letting it oscillate the way it wants to. Right? However, it's certainly possible to force a system to oscillate in a certain way. And in that case, you have to apply a periodic force, which is a driving force, which is called a driving force. And that would force the oscillations to happen in a particular way. Right? So if you apply a driving force, then the frequency of the driving force is what will determine the frequency of the oscillations. And so in that case, the frequency of the oscillations would be different than the natural frequency. Right? So let me give you an example. Suppose you take a pendulum and then you just let this swing. So you just swing it to one side and let it go. Then it will just oscillate at its natural frequency, which you now know omega is equal to square root of G divided by L. It just comes from the same analysis that we did when we calculated the time period. So that is going to be the natural frequency of a simple pendulum. However, suppose every time the pendulum gets over here, you sort of give it a push. Right? So in that case, you're applying a driving force, a periodic driving force. Periodic because you're applying the push every time the pendulum gets to one side. So here's the pendulum. It comes over here, you give it a smack, and then it goes back and it comes over here, give it another smack. So if you do that, that is an example of a driving force, right? And the frequency of the driving force is, in this case, is just the same as the frequency of the pendulum because you're giving it a smack every time the pendulum completes one period, right? However, you could have given, the driving force could have had a different frequency. So I could have just kept pecking at the pendulum as it goes like this. So I could have done that. And in that case, the driving force would have had a different frequency. So my point is that a system, if it's just allowed to oscillate on its own, will just oscillate at its natural frequency. And that's completely determined by the properties of the system itself. Right? However, it can also be driven with a periodic force, in which case its frequency will try to match the frequency of the driving force. Right? Now, there's a very interesting phenomenon here. Suppose you do try this. Suppose you have a pendulum, and this is something I show in class, and it's really, really fun to, students really enjoy watching it. I wish I could show that demonstration now. Suppose I take a pendulum and let it swing, right? And then I keep on pecking at it like this. How do you think the pendulum is going to behave? The result is you'll find that there is no motion at all. The pendulum hardly responds at all. So if I keep on pecking at it at various frequencies, either fast or slow, the pendulum just chaotically responds and doesn't really do anything. The best way to make the pendulum go is to give it a driving force. You make the driving force have exactly the same frequency as the pendulum. So I do this, comes back, give it a smack, give it another smack. So in that case, the frequency of the driving force matches the frequency of the natural frequency of the system, the frequency of the pendulum. When that happens, when the frequency of the driving force matches the natural frequency, something amazing happens. The amplitude of oscillations becomes very large, right? So in this example, if I keep smacking the pendulum each time it comes to one side, which means the frequency of the driving force and the frequency of the pendulum match, what I'm going to find is that the amplitude just keeps on increasing and the pendulum just keeps on swinging to larger and larger amplitudes. This phenomenon is called resonance. So it's as if the system is really happy when the force that's driving it is driving it at the same frequency that the system likes to oscillate. So this is called resonance. And a simple example of resonance is the one that I just talked about. And it's also an example that you're very familiar with. If you remember being on swings when you were a kid, you remember that in order to make the swing to very large amplitudes, what you would do is you would just keep giving it small pushes every time the swing came back over here, right? So here's the swing like this, it goes like this, comes back, and another kid gives it a push. And so if you keep doing this, you can make the amplitude really large, right? So essentially you're using the phenomenon of resonance. You're making the frequency of the driving force match the natural frequency of the system. And you're making and that makes the amplitude of the oscillation tremendously rise up. There are many, many applications of resonance. I'll talk about a few applications very briefly. So one application is the following. There are certain circuits, and you're going to learn about this at the end of physics 2. There are certain circuits, electrical circuits. This is probably not going to make any sense to you now, but I'll just draw an example of a circuit like that. This is just a very simple electrical circuit which consists of something called an inductor and a capacitor, and maybe also a resistor. So if you have a circuit like this circuit has a natural frequency. So if you let the circuit go, the current will just oscillate back and forth through the circuit, right? Just like a simple harmonic oscillator. And amazingly, the mathematics of that exactly matches the mathematics of a simple harmonic oscillator, right? So this circuit has a certain natural frequency. Now, suppose this circuit is connected to an antenna, and I'll just draw the antenna over here. That thing is the antenna. So suppose this circuit is connected to an antenna, and let's say that it's this particular circuit, nothing is happening. Like you just have the circuit lying here. You've not put any energy into it or anything. Let's say that you've got another circuit somewhere over here, which is identical to this one, and it also has an antenna. And what you do is you set this circuit number 1 going. So you make the current oscillate in circuit number 1, right? So when you make a current oscillate, as you learn in physics 2, it puts out something called an electromagnetic wave. So a wave will start flying out into space, into space really, in all directions. And what is that electromagnetic wave going to do? So when it hits the antenna of this circuit, if the frequency of circuit number 1 matches the natural frequency of circuit number 2, then circuit number 2 will light up and the current will start flowing through circuit number 2 as well, even though there is no battery or anything in circuit number 2. So circuit number 2 will respond to circuit number 1 if their natural frequencies match. So suppose the frequency of this one is 100 hertz and the frequency of this circuit is 100 hertz. Then all you have to do is get circuit number 1 going, the current oscillating in circuit number 1. The antenna is going to radiate out an electromagnetic wave of the same frequency, 100 hertz. And that electromagnetic wave is going to hit the antenna of circuit number 2. And amazingly, it's going to make circuit number 2 also start oscillating. So there will be a current going in circuit number 2 as if you put in a battery in there, which you didn't. And so that is one way you can send signals from one point to another. And at a very elementary level, that is how any radio works. So that's how radio transmissions work, right? Okay, but what if this was 100 hertz and this was 110 hertz? Then circuit number 2 wouldn't respond at all. It would only respond if its natural frequency matches the frequency of the electromagnetic wave that's coming in. So when you are changing the station of your car radio, what you're doing is you're changing the natural frequency of the circuit inside the radio, right? And by making it match different frequencies, you can pick up different stations. So you know that all these stations, radio stations, have numbers like 90.3. What is 90.3? Or 107.5. These are all numbers of radio stations in Nashville. So what do these numbers stand for? 90.3 stands for 90.3 megahertz. Mega is 10 to the power of 6. And that is really the frequency of the electromagnetic wave that that particular station puts out. So if you tune the circuit of your radio to that particular frequency, then it's going to pick up that electromagnetic wave, and the circuit will come alive. It will start responding to that electromagnetic wave, and you'll be able to and if you send so the current in your radio circuit will start responding to that, and if you feed that into a speaker amplifier and a speaker, then you can hear the sound that's being broadcast by the station. So that is the principle of radio transmission. It depends on the phenomenon of resonance. So you know that the sun puts out electromagnetic waves. You're going to learn what electromagnetic waves are in physics too. The sun puts out electromagnetic waves of various frequencies. Some of these electromagnetic waves that have a characteristic length. For any wave, this length is called, this is the wave, this length from peak to peak is called the wavelength. So some of the electromagnetic waves that the sun puts out have wavelengths between 400 to around 750 or something like that nanometers. You know what a nanometer is? It's 10 to the power of -9 meters. So those particular waves are what we call visible light. So when these waves hit our eyes, we have the sensation of sight. Our eyes are a detector for this type of electromagnetic wave. Our eyes don't respond to any other kind of electromagnetic waves. Though in principle, you can have electromagnetic waves of any wavelength, right? So the sun puts out electromagnetic waves of various types, but mostly visible light. So this is what we call visible light. And it also puts out electromagnetic waves of a longer wavelength, and those are called infrared. So infrared waves have a longer wavelength than visible light, right? Infrared waves are what we associate with heat. So you know that the sun produces heat, gives us warmth. So when you stick your hand out into the sun, that sensation of warmth that you get, suppose you're standing in the shadow and you put your hand out into the sun, the sensation of warmth that you get on the skin is basically the infrared radiation coming from the sun. Our skin has some sensors to sense infrared radiation. Whenever you're standing near something very hot, like if you're standing in front of a fire or something, the warmth that you feel coming from the fire is called is infrared radiation. Look, our TA is here. So that's infrared radiation. Okay, oops, wait a second. All right, so now basically what happens is that the sun sends out infrared radiation, sends out a lot of visible light and infrared radiation, but we absorb the visible light as well as the infrared radiation, and we immediately re-emit energy in the form of infrared. So, so if there's a tree over here, and if I'm standing over here, or Tori is standing over here, here she is, then all of us are giving off infrared radiation, right? See if I can draw Tori. All right, okay. So all of us are giving off infrared radiation. You are also giving off infrared radiation. Everything around us is giving off infrared radiation, right? So if all of this infrared radiation were allowed to escape into space, what would happen to the Earth? The answer is the Earth would become extremely, extremely cold. In fact, the Earth would be so cold that all the oceans and all bodies of water on the Earth would be frozen solid. So how is it that our planet is so nice and warm and warm enough that water can exist in liquid form? The answer is because of a certain molecule in the atmosphere, the carbon dioxide molecule. So the carbon dioxide molecule, as it turns out, has several frequencies, right? So what I'm tremendously simplifying things here. Basically, if you send any kind of electromagnetic radiation, all electromagnetic radiation has a particular frequency. So it turns out that there are certain frequencies. If the carbon dioxide molecule encounters those frequencies, it absorbs that electromagnetic radiation. So it's excited only by those frequencies, right? And so that's kind of another example of resonance. So it turns out that infrared radiation matches one of the one of the frequencies, one of those specific frequencies for the carbon dioxide atom. And so the carbon dioxide captures the infrared radiation and immediately re-radiates it. So here's our little carbon dioxide molecule. When infrared comes in, the carbon dioxide captures it and then immediately re-radiates it. So the infrared is not allowed to, all of it is not allowed to escape into space. Some of it is sent back into the atmosphere. And that has an amazing effect. It sort of holds, traps the warmth in our atmosphere. So this is called the greenhouse effect. And this is the reason why carbon dioxide is called a greenhouse gas. Carbon dioxide is not the only greenhouse gas. Water is also, water vapor is also a greenhouse gas. Methane is a greenhouse gas. And so these greenhouse gases have the effect of trapping heat in our atmosphere because of a phenomenon which is similar to resonance. Right? And you know that, of course, we have a problem now, which is that we have pumped too much carbon dioxide into the atmosphere. And so we are trapping in too much heat in the atmosphere. And that's what's called global warming or climate change. All right, so that's just another application of this. So we are going to stop the chapter over here. You are not responsible for either damped oscillations or forced oscillations. And so essentially, you are only responsible up till, oops, you're only responsible up till this slide over here, the physical pendulum. That's the last topic that, yeah. So you can skip the discussion. The discussion of damped and forced oscillations is not something that you are responsible for. All right.